So static compensator. So by varying the amplitude of output voltage. So last class we have seen. So just we have considered that synchronous machine, working of synchronous machine, how it generates or absorbs the reactive power. So the concept of that one will be used in statecom. So in statecom, instead of that rotating part, it will be replaced by VSC, voltage source converter. Okay, so this is what you have. So by varying the amplitude of output voltage produced, the reactive power exchange between the converter and the AC system can be controlled. Okay, so this similar to that of synchronous machine. So in this case, what you have, if the voltage VO is greater than V, that VO is, we'll see this. So this is your VO. This VO is the output voltage of statecom. If this is greater than this system voltage or point of common coupling voltage, this PCC voltage, what happened? It will generate the reactive capacitive power for the AC system. That means current will flow from this statecom to the AC system. Okay, so that this is what you have. So first case. No? Then second case, if VO is less than V, then reactive current will flow from AC system to the converter. That is your inductive power. So system will absorb, or the converter will absorb, or system will supply the power. Then if VO is equal to V, then there is no power exchange in the system. So this is the case. Okay, so if VO is greater than the current will flow from the system to the statecom converter. Okay, so this is the case. So this is point of common coupling. Yeah. Now vector diagram of the statecom, let us see. So let V is equal to statecom converter output voltage, then V is equal to common point of common coupling voltage, then IL is the load current, IO is the statecom injected current, then IS is the compensated source current, so X coupling inductance. So now if you see, this is for the capacitive mode. So capacitive mode means here VO is greater than V. So in this case, what will happen? It will draw a current which is capacitive in mode. So this current, it will draw this current capacitive in mode. Say suppose this is our load current, so which is lagging in nature. So load current, our load current, lagging load current, which is actually very much common in present industrial application. So this is the case of this. So now this is lagging. Now our main aim here is to maintain this compensated source current at a unity power factor or near to the unity power factor. So in this case, so now what will happen is, now say suppose our current is here, IL is here. Now what will happen? So now in order to make this unity power factor or near to unity power factor, what we have to do is we have to increase this VO so that it will supply increase current, thereby maintaining this IS, unity IS, this the angle between the voltage and this one will be unity. So this is the very much common like load pattern of the present day and the industries and all this thing, lagging power. Now if the power system is drawing a leading power factor, which can be actually compensated by the statecom. Okay, so if it is this leading power factor, then what will happen? So this is your leading power factor. This is very rare, but if it draws like that, then IL leading, that is, this is for inductive mode. So that is your VO second mode. No, VO is less than V. Okay, then there what will happen is system will supply current to the, so this system will, the network will supply current to the statecom. So in the first case here, this STATCOM will supply current to the AC system. Here system will supply. Okay, so in this case, system will supply current to the STATCOM when V is less than when V is greater than VO. Okay, so that is what you have. Then if you can just see comparison between the synchronous condenser and the STATCOM, what you have. So you can here synchronous condenser nadi rotating part is there, whereas STATCOM nadi you have is switches are there. Okay, so switch is there. So this is there. So first synchronous condenser rotating part is there, but whereas in this static switch are there. So that main difference running. Then compared to SC, STATCOM output voltage also contain many harmonics, okay, and some methods. So this is the drawback of this. So what you have to do is you have to use PWM, pulse width modulation, or multi-pulse or multi-level inverter, etc. has to be used to illuminate them. So STATCOM will generate harmonics compared to that of a synchronous condenser, and therefore it requires this other converters to mitigate the harmonic content in this. Then advantages of STATCOM over SVC. So some of the advantages of STATCOM over SVC are: first one is faster in response, then it requires less space, okay, less space. Then another one is inherently modular and relocatable, so it can be relocated anywhere, means smaller in size bending. Then it can be interfaced with real power sources, so means we can use this real power source of this compared to SVC. Then STATCOM has superior performance during the low voltage condition, as the reactive power can be maintained constant. So that is another advantage of this. Then advantage of STATCOM over SC synchronous condensers are: response is much faster, okay, to the fault conditions. So system changing condition are fault condition. Then it does not contribute to short circuit current. So another advantage here. It has a symmetrical lead lag capability. So symmetry. So lead and lag. So maximum and minimum lead lag current will be same symmetry. Then it has no moving part, and hence maintenance is easy compared to that synchronous condenser. Then this STATCOM will have it will not lose its synchronism under major disturbance, whereas this under major disturbance, this synchronous condenser will have loss of synchronism. So they will lose its synchronism is in case if they are operating in parallel. Okay, so that is what you have. So these are some of the advantages of STATCOM over this synchronous condenser. Then another point you can have is in synchronous static compensator, it is possible to equip the converter with DC source, means STATCOM with storage like such as battery or SMES you can have. So you can connect any of this one to the STATCOM. Then in this case, what will happen if you have this battery or storage can, then what will happen is this converter can be used to control both reactive. So reactive you can control without battery, but if you connect battery, then the real power can also be controlled. Active as well as reactive power can be controlled or exchanged with the AC system. And hence this, when it is connected with the storage system, it will function as a static synchronous generator, SSG. Okay, so then we call it as SSG, static synchronous generator, when it is connected to or when the STATCOM is connected with the external DC source. And then here, why the advantage or what are the applications of the controlling real power as well as the reactive power is it can be used effectively in power oscillation damping, first application. Then second one is peak power leveling, and then providing uninterrupted power for critical loads. So these are three applications in which both real and active power control by STATCOM. So here you have this is the case. Otherwise everything is there, voltage source converter, VAC, everything. So now here you have if you disconnect this, just a normal STATCOM. So where only STATCOM with internal. So this sorry, this one, so bulk is there. So this is the case. Okay, so this energy storage, you disconnect this, then you will get a normal STATCOM where only reactive power control can be there. So here you have if VO is greater than VAC, then what will happen is the power will be supplied by STATCOM. If VAC is greater than VO, power will be supplied by AC line to the STATCOM. But now since here we have the energy storage system. So this energy storage system, with the introduction of energy storage system to the STATCOM, what will happen is it will exchange the active power among the transmission line and the STATCOM. So this is another advantage of this STATCOM. Okay, so it can be used to control both reactive as well as active power. Okay, so now you can keep in mind is to exchange the real power with the system, AC system. So what we have to do is we have to have a phase shift between the converter output voltage and the point of common coupling voltage. So there should be phase shift. This VAC and VO or VDC. There should be a phase angle difference between this. Okay, so now we will see is if VO leads V, means if stator voltage, STATCOM voltage leads the transmission line voltage, then real power is supplied to the bus. Then if VO lags V, then real power is absorbed from the system, means absorbed by the STATCOM. So this is one. So now if you see this, STATCOM can be operated as independent control of real reactive power. That is, it can be operated as a four-quadrant operation here. So if you see this four-quadrant operation at AC terminal, what will happen is this is IAC. So IAC can be later on while coming to the control part, you will see this IAC is resolved into two parts. One is active component. This is your reactive component. Okay, so now when VAC is greater than or less, when VAC leads this, so what happened? It supplies power here in quadrant 1 supplies active and reactive. Quadrant 2, what happened? Real power is absorbed. Means what it does means, what real power absorbed means, it is here, means VO is lagging behind V, but it supplies Q, means supplies Q means here VO is greater than, supplies Q means VO is greater than V, and then VO here VO lags. Okay, lags V. In this case, it is supplying means VO is greater than V, and then VO leads again here. VO leads V. Okay, so that is what you have. Then here again, P is absorbed. So when P absorbed means VO lags V, and then absorbs Q means V is greater than VO. So here supplies P means VO leads V, and then absorbs Q means what it means, Q, it absorbs Q means V is greater than VO. So in this case, V is greater than VO. So same thing here at DC terminal. Yeah. So this is how the STATCOM can be used to control both active as well as reactive power in the system. Now the control of STATCOM, we can see, we'll try to see control. So static war generator converter means STATCOM comprises a large number of GTO switches. Okay, so gate thyristor switches. Then the gating command for these devices are generated by, so we have the GTO are there, thyristors are there. So it can be generated by internal converter control. Okay, so this is first one, internal converter control. And then the reference signal is provided by external or system control. Gating command is provided by internal control, and then reference signal is given by, you have to give this reference signal, external signal. So reference is from the external point of view. Okay. Then another point you can just see is the internal control is an integral part of the converter. Okay, so this internal is the very much means like main part of the part, and its main function is to operate. So its main function is to operate the converter power switches so as to produce the synchronous output voltage that forces the waveform that reactive as well as real power exchange required for the compensation. So this is the main function of the internal control key. Okay, so this is what you have. So as illustrated here in this figure, you have the internal control achieves this by computing the magnitude of the phase angle of required output voltage from IQ ref or IP ref. Okay, so this is your, so IQ ref means this you have to give it external. This means this you have no this IO. Later on when you have this IO will be decomposed or resolved into two parts. So this part one IQF, and then another one will be IPF. Active current reference and reactive current reference. Okay, and then provided by this, which is actually given to the gating generator. Okay, so this is what you have. So direct and indirect method. So you have this energy storage, all this thing will be there. So now we have two types. So first one, internal control can be achieved by indirectly via controlling the DC capacitor voltage. Okay, so first one is indirect method, which can be used by controlling the DC voltage capacitor, indirect method. And another one you have is direct method, which can be used by using the PWM technique. Okay, so another one is this. So first one is direct method, indirect method, which is controlled by controlling the DC capacitor voltage, and second one is by direct method, which is used by using the voltage control mechanism. Example is PWM, so pulse width modulation technique. So you're modulating the pulse of that. So same thing, yeah. Then so now you can see is the basic approaches, direct and indirect methods are used here. So direct control and indirect control. So this is your indirect control. Okay, so indirect control, and then this is your direct control. Okay, so direct control, indirect control. Then indirect control method, just you can see. So this is your indirect control method. Loop is there, indirect control method. So the input to the internal control R for indirect control key. So the input R, what you have, input, what you have. So you can see is AC system bus voltage. So this one. Another one is output current of the converter. So this one. And last one is reactive current reference, this IQ reference. So these are the three input to the indirect internal control method. So now we will see one by one. The voltage V operates a phase lock loop that provides the basic synchronizing signal angle A. So actually this voltage will actually operate this signal, this comparator. Okay, so the comparator, which will actually that is actually this will generate this, and then it will compare it, and then this alpha later on we'll see this. Then output current IO is decomposed into its reactive and real component, and this reactive current is compared with the reactive current reference. So this external one, so your external one, it is compared with this, and then this one is fed to the error amplifier. Basically this error amplifier is either PI controller or PID controller, and then the output of this amplifier is del alpha. Then this del alpha is again compared with the output of phase lock loop PLL, and then you get this del alpha plus theta or theta plus del alpha, and then it is given to the gate pattern logic circuit. From there it will be given to the this. So then the gating circuit of this converter will be initiated, whereby it will start firing it. Then you change this firing angle alpha, and then the generation and absorption of power can be achieved. So this is how it functions, the controlling. Okay, so then you see is thus the obtained after suitable application angle del alpha. So this alpha, which defines the necessary phase shift between the output voltage of the converter and the AC converter system voltage needed for power discharging. So this is what I have explained you earlier. Then the angle del alpha is summed to this theta to provide this, which represents the desired synchronizing signal for. Okay, so this is your gate signal. So like you have this thyristor version, this is there. So here the signal is given by this gate lock pattern logic. So gate signal is given by this. So here it is given is that it operates the gate pattern logic that provides the individual gate drive logic signal. Okay, so this is how the gate operator is operated, or gate logic is operated there. So basically this is a PI controller. Then another method you have is direct control. So direct control, you can see, is here. So you see the direct control. Then similar to this direct control, inputs are, we have is AC system bus voltage. So this output current, this reference, this is given by external means. All are internal. This is external. Then DC voltage VDC. So this is it. So addition to 3. So these 3 are common for both direct as well as indirect, but additional we have is VDC here. So till here it is common. So if you see, if you recall back, then it is same. Now 4th one you have is DC voltage reference. So this voltage DC actually reference determines the real power of the converter that must be absorbed from the AC system in order to supply its internal losses. So this is how it will. So similar to that indirect control, the converter output current is decomposed into 2. So this one, 2, that is this part and this part, IOQ and IOP. So real and output power, reactive, output current, active. Okay, so P stands for active, Q for reactive. And these components, so these 2 components are compared to the external reactive current. Okay, so external reactive current, IP reference, IQ reference, and the internal real current reference derived from the DC voltage regulation loop. Okay, so what it is doing is, so these components are compared to the external reactive current. So IOQ is compared with IQ reference, and IOP is compared with this VDC reference, or this. Okay. So this one, it is compared here. 2 comparators are there, comparative. Okay, so here now you have that figure. So here you have is direct control. Now you can see after suitable amplification, so this amplifier, the real and the reactive current signal are converted into the magnitude and angle of the wanted converter output voltage from which the appropriate gate derived. So this is it. Now here the output of the pure PI controller in this case. So here IO is decomposed into this, and IO will compute what amount of reactive current required to feed, thus will compare with IQ reference and feed to the error amplifier PI or PG controller. This is their first one. Then second one is also we require to maintain the DC bus voltage. So because of that we are giving the DC voltage, and then DC voltage is fed compare to the amplifier and then compare with the IOP here, and then again. So because of this, the output of this error amplifier and this error amplifier is different. So output of this error amplifier, this amplifier is fed to the magnitude and angle computer, whereby it will generate angle alpha and then voltage VO. Okay, so it will generate VO, and then this angle alpha, then PLL, this phase lock loop will generate theta, and this theta is summed with angle alpha and then given to the gate logic pattern, and that gate logic pattern will be fed to this gate signal, and then it will actually generate the signal which will be given to the converter to fire up the GT or IGBT present in this one. So this is how again the direct control methods are used. Okay. Hello.
Yes, sir. Okay,
Yes,
sir.
Yes, sir.
Or dois gitsin.
Maya oila, sir.
Roshan.
Inla, sir.
Roshan, emi na dachile emi. So Dojgitsin and Sonamazer is not there, no? Dojgitsin, Sonamazer and Killiwangchu.
Doji ke se o deila, sir. Koi yani net ki be darwani left the conversation se thina, sir.
Kilowatts heading, sir.
Ah? Killiwangchu. Okay, okay. 20. 1920. Sonamazer on ya mao. $20 means 19, 1, 2, 3, 4, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So those gates and then Mindum.
At an hour, sir. Net
Ah?
problem there. Doji ke se at an hour. Net problem dina.
Okay. Sonamazer is not there. No? Okay, so we'll stop here. Thank you. So next class, we'll continue in the next class.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.